Chapter 5 looks at how bivariate regression works. And we've already looked at bivariate regression in the material for April 6th, but I think that it's useful to use this chapter to review the process for bivariate regression before we move forward to talk about the logic and process of multiple regression. So I'll only make a couple of notes since a lot of this is review from what we've done in previous weeks. Allison points out that in general, we say that the correlation coefficient R measures the degree of scatter around a regression. Right? You know, how much scatter is there, how close it is to the line, and so on. The slope coefficient for regression, the slope coefficient B, measures the steepness of that regression line. So what I want to talk about a little bit is how regression is related to correlation. So correlation is actually called the Pearson's product moment correlation coefficient. And it has a very close relationship to the regression line. Correlation is equal to the covariance of X and Y divided by the standard deviation of X multiplied by the standard deviation of Y, right? So this is a very simplified formula that condenses down what all of those components are actually talking about. So that's your correlation coefficient. Your regression coefficient is the covariance of X and Y over the standard deviation of X squared. Right, this is a bivariate example where you only have one independent and variable predicting a dependent variable. But look at what's similar between these two. So what's important is that R and B have the same numerator. So the covariance is the same. This means that testing the correlation is equal to 0 is the same as testing the slope is equal to 0, right? So Allison argues in the text that there's no need for two separate tests here. So that if we are testing the hypothesis that the covariance is 0, we're doing the same thing. And so we can actually use, for bivariate regression only, we can actually use the R value and square it. And it's the same as our R squared value. So in bivariate regression, R squared is the same as the squared correlation between X and Y. This is not true of multiple regression since each individual independent variable will have its own correlation, its own B value. But it is true for bivariate, where you have a single independent variable affecting a single dependent variable. In addition, both statistics measure linear relationships. Correlation measures it linearly. Linear regression measures these relationships linearly. And so both are problematic if we're trying to explain nonlinear relationships. Allison also talks about the calculation of standard error, and he gives a more complex formula here compared to the one that we used earlier in the semester, right? So the standard error formula was the standard deviation of the square root of n, right? Or n-1 if you have small samples. For the regression equation, it's more complicated, but some of that same information is there. And so there's some connection between those things. The real difference is the notation of and the elements of the equation, but he also wants you to see that there is a relationship between these two. So we have n-1 because we're dealing with one variable. We have n-2 because we're dealing with two variables. We have y and z now instead of just one. And so this is your R squared for X and Y, and then we have those additional notations. So it's similar to that S of Y multiplied by, and so there are similarities between these two. As we move from one independent variable to two independent variables or more, the math gets a lot more complicated. And when we have two independent variables, we essentially run through a three-step process. First, we regress y on z, that is, take the y as the dependent variable and z as the independent variable. So in our equation, x and z are independent variables. But if we were going to do this by hand, we would run multiple sets of bivariate regressions. So we would regress y on z, with y as dependent and z as independent, we'd calculate the residuals from that regression and call it y star or y prime. Then we would regress x on z. So we would regress x on z and calculate those residuals and call those x prime. And then we would regress y prime on x prime. The slope from that third regression, the slope that we get from here, is exactly the same as if we had done the full-blown regression model. So I'm not going to ask you to do these hand calculations. What I'm most interested in is that you understand the results are partial correlations. So we can calculate the correlation, the regression between x and y, and the residuals from that bivariate regression on x, and that correlation is called a partial correlation and can be written as r sub x, y, z. Okay, so it's a partial correlation of x, y on z. The inclusion of partial correlation allows us to examine the relationship between an independent variable and the dependent variable while holding one or more of the independent variables constant. And we can do this in order to determine if a correlation among independent variables may be creating unexplained variance or error or disturbances in the equation.